Welcome to Dark Cosmos Theory, where we unravel the mysteries that lurk in the vast darkness of space. Tonight, we're going to explore something that hangs in our night sky, visible to the naked eye, yet so incomprehensibly massive that your mind will struggle to grasp its true scale. We're talking about the Andromeda Galaxy, our closest galactic neighbor and the largest member of our cosmic neighborhood. But here's what will blow your mind. This isn't just some distant object to admire. Andromeda is hurtling toward us at over 100 kilometers per second, and the collision is inevitable. Before we dive deep into this cosmic mystery, I want to hear from you. Where in the world are you watching from right now? Drop your location in the comments, whether you're in Tokyo, New York, Mumbai, or anywhere else on this pale blue dot we call home. It's fascinating to think that people from all corners of Earth are joining together to explore the same distant galaxy. And if you're new here, make sure to hit that subscribe button and ring the notification bell, because we're about to embark on a journey that will fundamentally change how you see the night sky. Let me start with something that should shake you to your core. On a clear, dark night, far from city lights, you can see the Andromeda Galaxy with your naked eye. Think about that for a moment. Without any telescope, without any equipment, you can see a collection of 1 trillion stars located 2.5 million light-years away. The photons hitting your retina right now left Andromeda before humans learned to control fire, before we built the first shelters, before we were even recognizable as modern Homo sapiens. You're literally looking back in time, witnessing light that has been traveling through the void of space since our ancestors were barely learning to walk upright. But here's where it gets absolutely mind-bending. That faint smudge of light you can barely see? It's actually bigger in the sky than the full moon. Yes, you heard that right. If your eyes were sensitive enough to capture all of Andromeda's light, it would span an area 6 times wider than the full moon. The galaxy is so enormous that even from 2.5 million light-years away, it dominates a huge portion of the sky. We just can't see most of it because our eyes only detect the brightest core, missing the vast spiral arms that stretch out into the cosmic void. The Andromeda Galaxy, catalogued as Messier 31 or M31, is not just big, it's a monster. We're talking about a spiral galaxy that stretches 220,000 light-years across its disk. To put that in perspective, if you could travel at the speed of light, the fastest speed possible in our universe, it would take you 220,000 years just to cross from one side to the other. And remember, at light speed, you could circle the Earth 7.5 times in just 1 second. The scale we're dealing with here transcends human comprehension. Let's talk numbers, because sometimes raw data is the only way to begin grasping this cosmic leviathan. Andromeda contains approximately 1 trillion stars. That's 1,000 billion suns. If you started counting 1 star per second right now, you'd need more than 31,000 years to finish. And by then, millions of new stars would have been born and millions more would have died. Each of those trillion stars is potentially orbited by planets. If even a tiny fraction have planetary systems like ours, we're talking about trillions of worlds. Rocky planets, gas giants, ice worlds, each with their own moons, their own unique characteristics. The sheer abundance of cosmic real estate in Andromeda alone is staggering. But stars are just the beginning. Between those trillion suns lies an intricate web of dust and gas, the raw material for future generations of stars. Massive clouds of hydrogen stretch across hundreds of light-years, dark nebulae that obscure the starlight behind them, glowing emission regions where ultraviolet radiation from young stars ionizes the surrounding gas, making it shine in brilliant reds and pinks. This interstellar medium isn't just filler, it's the lifeblood of the galaxy, the substance that allows Andromeda to continually renew itself, to birth new stars, to evolve and change over billions of years. And then there's the dark matter. This is where things get truly mysterious. Everything we can see in Andromeda, all those trillion stars, all that gas and dust, all of it accounts for less than 20% of the galaxy's total mass. The rest? It's dark matter, an invisible substance that we can't see, can't touch, can't directly detect, but we know must exist because of its gravitational effects. Andromeda is wrapped in a massive halo of dark matter that extends far beyond its visible disk, perhaps stretching for over 1 million light-years. This invisible cocoon outweighs all the stars combined, shaping the galaxy's structure, governing the motions of its stars, holding the entire system together through gravity alone. The total mass of Andromeda, including all this dark matter, is estimated at somewhere between 1.2 and 1.5 trillion times the mass of our Sun. Think about that. Our Sun, the star that makes life on Earth possible, that burns with the energy of 400 trillion watts, that has enough mass to fit 1.3 million Earths inside it, is just a single unit of measurement, and Andromeda contains the equivalent of more than 1 trillion of them. At the very heart of this galactic behemoth lurks something even more extreme, a supermassive black hole weighing in at approximately 100 to 200 million solar masses. This is a region of space-time where gravity has become so intense that not even light can escape. The event horizon of this black hole, the point of no return, would be larger than our entire solar system. Around it, stars orbit at incredible speeds, whipping around the galactic center in frantic dances governed by the immense gravitational pull. Some of these stars move so fast that they complete an orbit in just a few million years, despite being farther from the black hole than Pluto is from our Sun. Now, let me paint a picture of what Andromeda actually looks like up close. Imagine you could somehow travel there instantaneously, approaching the galaxy from outside. What you'd see would take your breath away. A magnificent spiral structure dominates your view, with 2 major arms and several smaller ones sweeping out from a bright yellowish-white central bulge. These aren't solid structures, but rather density waves, regions where stars, gas, and dust have bunched up due to the complex gravitational dynamics of the rotating galaxy. The spiral arms are where the action happens. In visible light, they glow with the blue-white fire of massive young stars, some burning 100 times brighter than our Sun. These stellar giants live fast and die young, burning through their nuclear fuel in just a few million years before exploding as supernovae. Interspersed among them are the red and pink glows of emission nebulae, vast clouds of hydrogen gas illuminated by the ultraviolet radiation of nearby hot stars. Dark lanes of dust cut across the arms like cosmic highways, blocking the light from stars behind them, but hiding within them the seeds of future stellar generations. The central bulge of Andromeda tells a different story. Here, the light is yellower, more subdued. This is the domain of older stars, red giants and yellow dwarfs that have been burning steadily for billions of years. The stars here are packed much more densely than in the outer disk, sometimes separated by distances of just a few light-years instead of the several light-years typical in the spiral arms. If you lived on a planet in the bulge, your night sky would be crowded with brilliant stars, so many that you might never experience true darkness. As you move outward from the visible disk, you'd enter the halo, a vast spherical region filled with globular clusters and streams of stars. The globular clusters are dense balls of ancient stars, some containing hundreds of thousands of suns packed into regions just a few dozen light-years across. They orbit through the halo on long, elliptical paths, taking hundreds of millions of years to complete a single orbit around the galactic center. The streams, meanwhile, are the remnants of smaller galaxies that Andromeda has torn apart and consumed over its long history. They trace delicate arcs through space, fossil records of cosmic cannibalism. Speaking of cosmic cannibalism, Andromeda isn't alone out there. It's surrounded by a family of satellite galaxies, smaller companions bound to it by gravity. The 2 most prominent are M32 and M110, both elliptical galaxies visible even in amateur telescopes. M32 is compact and dense, possibly the stripped core of a once larger galaxy that ventured too close to Andromeda and paid the price. M110 is more diffuse, showing signs of recent interaction with its giant neighbor. But these are just the tip of the iceberg. Andromeda has dozens of smaller dwarf galaxies orbiting it, many so faint they've only been discovered in the last few decades. Some contain just a few million stars, cosmic minnows swimming in the shadow of a whale. The relationship between Andromeda and its satellites reveals something fundamental about how galaxies grow and evolve. Galaxies don't form in isolation and then remain unchanged. They're dynamic systems that constantly interact with their environment, capturing smaller neighbors, stripping them of their stars and gas, growing larger through merger after merger. Andromeda bears the scars of this violent past in its structure. Astronomers have detected ripples and warps in its disk, asymmetries in its spiral arms, all signs of relatively recent gravitational encounters that disturbed its equilibrium. One of the most fascinating discoveries about Andromeda came from detailed observations of its rotation. When astronomers measured how fast stars orbit at different distances from the galactic center, they found something that didn't make sense based on the visible matter alone. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just as outer planets in our solar system take longer to complete an orbit than inner planets. But that's not what they observed. Stars in the outer reaches of Andromeda were moving much faster than expected, so fast that they should have been flung out into intergalactic space by centrifugal force. There was only one explanation: invisible mass. Lots of it. The dark matter halo surrounding Andromeda provides the extra gravitational pull needed to keep those outer stars in their orbits. This was some of the earliest and most compelling evidence for dark matter's existence, a discovery that fundamentally changed our understanding of the universe. We now know that dark matter outweighs normal matter by a factor of about 5 to 1 across the entire cosmos. Galaxies aren't just collections of stars, they're islands of normal matter floating in vast oceans of dark matter. But what is this dark matter? That's one of the biggest unsolved mysteries in modern physics. We know what it's not. It's not ordinary atoms, not black holes, not any form of matter we can create in our laboratories. The leading candidates are exotic particles that barely interact with normal matter except through gravity. Particles with names like WIMPs and axions that might be streaming through your body right now without you ever knowing it. Despite decades of searching, we haven't directly detected these particles yet, but the evidence for their existence is overwhelming. Dark matter is the invisible scaffolding upon which the visible universe is built. Now let's talk about one of the most dramatic aspects of Andromeda. It's coming for us. I mentioned this at the beginning, but let me elaborate on what's actually happening. When astronomers measure the spectrum of light from Andromeda, they notice something unusual. Most distant galaxies show redshifted light, meaning they're moving away from us due to the expansion of the universe. But Andromeda's light is blue-shifted. It's moving toward us at approximately 110 kilometers per second, or about 250,000 miles per hour. At that speed, you could travel from Earth to the Moon in less than an hour. Why is Andromeda approaching when the rest of the universe is expanding away from us? The answer lies in gravity. On cosmic scales, space itself is expanding, carrying distant galaxies away from each other. But on local scales, within galaxy groups and clusters, gravity is strong enough to overcome this expansion. Andromeda and the Milky Way are bound together in a gravitational dance that began billions of years ago, and that dance will inevitably end in a merger. Based on current measurements and computer simulations, astronomers predict that Andromeda will collide with the Milky Way in approximately 4 to 4.5 billion years. Now, before you panic, let me clarify what collide means in this context. Galaxies are mostly empty space. The distances between stars are so vast that even when two galaxies merge, the chances of any two stars actually hitting each other are infinitesimally small. Instead, the collision will be a gravitational interaction on a grand scale. Here's how it will unfold. First, Over the next few billion years, Andromeda will grow larger and larger in Earth's night sky, assuming Earth still exists and has observers to witness it. What's now a faint smudge will gradually become a stunning spiral structure dominating the heavens. As the galaxies approach, their gravitational fields will begin to interact, pulling and distorting each other's shapes. Tidal forces will stretch both galaxies, drawing out long streamers of stars into intergalactic space. The first pass will be spectacular. The two galaxies will interpenetrate, their disks passing through each other like ghosts. But gravity doesn't let go easily. After passing through, both galaxies will slow down, stop, and fall back toward each other for a second encounter. This dance might repeat several times, with each pass mixing the two galaxies more thoroughly, until finally they settle into a single, merged system. The merger will trigger massive bursts of star formation. When giant clouds of gas from the two galaxies collide, they'll compress and heat up, causing them to collapse and form new stars at a prodigious rate. Regions that were once quiet will light up with the blue-white brilliance of thousands of newborn massive stars. The galaxy will briefly become what astronomers call a starburst galaxy, forming stars at a rate hundreds of times higher than in normal spiral galaxies. Meanwhile, the two supermassive black holes at the centers of the Milky Way and Andromeda will begin their own cosmic dance. As the galaxies merge, the black holes will spiral inward, shedding energy through gravitational interactions with nearby stars. Eventually, after perhaps a few 100 million years, they'll merge in a cataclysmic event that will send gravitational waves rippling across the universe. The resulting black hole will weigh somewhere between 200 and 300 million solar masses, making it one of the most massive black holes in the local universe. The final product of this merger won't be a spiral galaxy anymore. Computer simulations suggest it will be a giant elliptical galaxy, a smooth, football-shaped distribution of stars with no distinct spiral structure. The elegant spiral arms that characterize both the Milky Way and Andromeda will be scrambled and destroyed in the chaos of the merger. Some astronomers have already given this future galaxy a name, Milkomeda, a portmanteau of Milky Way and Andromeda. What does this mean for Earth? Well, first, it's worth noting that by the time the merger occurs, Earth might not be habitable anymore. Our sun is gradually brightening as it ages, and in about 1 billion years, the increased solar radiation will likely cause a runaway greenhouse effect that boils away Earth's oceans. But let's assume for the sake of argument that Earth or its successor civilizations are still around to witness the merger. The good news is that the solar system is extremely unlikely to be directly affected by a stellar collision. The distances between stars are just too large. What will change is our cosmic address. Instead of residing in the outer suburbs of the Milky Way, we might find ourselves in a completely different part of the merged galaxy. Our orbit around the galactic center will be radically altered, and the night sky will look completely different, filled with unfamiliar stars and nebulae. The merger of Andromeda and the Milky Way is just one example of a process that's common throughout the universe. Galaxies grow by merging, and the universe is filled with galaxies in various stages of collision. The Hubble Space Telescope and other observatories have captured stunning images of galaxy mergers, showing galaxies with distorted shapes, long tidal tails, and brilliant starburst regions. These cosmic train wrecks are some of the most visually spectacular objects in astronomy, and they give us a preview of what our own galactic merger will look like billions of years from now. But Andromeda's story doesn't begin with its future collision with us. It has a deep history of its own, one written in the motions of its stars and the structures we see today. By studying the chemical composition of stars in different parts of the galaxy, astronomers can piece together its evolutionary history. The oldest stars in Andromeda's halo formed more than 12 billion years ago, less than 2 billion years after the Big Bang. These ancient suns are metal-poor, meaning they contain very little of the heavy elements like carbon, oxygen, and iron that are common in younger stars. The reason for this is straightforward. When the first generation of stars formed in the early universe, they were made almost entirely of hydrogen and helium, the only elements created in the Big Bang. These stars lived out their lives, and when the massive ones exploded as supernovae, they synthesized and scattered heavier elements into space. The next generation of stars formed from gas enriched with these heavy elements, and they, in turn, produced more. Generation after generation, the interstellar medium became progressively more metal-rich. By studying the metallicity of stars in Andromeda, astronomers can determine when they formed and trace the galaxy's star formation history. What they've found is that Andromeda hasn't formed stars at a constant rate throughout its history. There have been periods of intense star formation interspersed with quieter epochs. Some of these bursts were likely triggered by mergers with smaller galaxies, events that funneled gas toward the center and ignited waves of starbirth. The galaxy we see today is the accumulated result of billions of years of evolution, a complex system that's constantly changing even though the timescales involved are so long that the galaxy appears static to human eyes. One of the most intriguing aspects of Andromeda is its structure at different wavelengths of light. In visible light, we see the spiral arms, the bright bulge, the dust lanes, but if we could see in infrared light, the view would be strikingly different. Infrared penetrates dust, revealing regions of star formation hidden in visible light. The Spitzer Space Telescope observed Andromeda in infrared and discovered something unexpected. The galaxy contains a series of concentric rings of dust, like ripples on a pond. These rings are thought to be the result of a collision with another galaxy millions of years ago, an event that sent density waves propagating through Andromeda's disk like ripples from a stone dropped in water. In ultraviolet light, Andromeda lights up with the glow of its hottest, youngest stars. The Galaxy Evolution Explorer telescope created stunning UV images, showing clusters of massive blue stars scattered throughout the spiral arms, highlighting regions where star formation is currently active. Many of these stars won't live long enough to complete even a single orbit around the galactic center. They'll burn through their fuel in just a few million years and explode as supernovae, enriching the interstellar medium with heavy elements and perhaps triggering the next generation of star formation. X-ray observations reveal yet another side of Andromeda. The Chandra X-ray Observatory has detected thousands of X-ray sources in the galaxy, ranging from supernova remnants to binary star systems, where material from a normal star spirals onto a neutron star or black hole, heating up to millions of degrees and emitting X-rays in the process. The central region of Andromeda emits faint X-rays from the vicinity of its supermassive black hole, though this emission is relatively weak compared to active galactic nuclei in other galaxies, suggesting that Andromeda's black hole is currently sleeping, not actively consuming large amounts of matter. Radio telescopes have mapped the distribution of neutral hydrogen gas throughout Andromeda using the 21 centimeter line, a specific wavelength of radio emission produced by hydrogen atoms. These observations reveal that the gas extends far beyond the visible stars, forming a disk that's significantly larger than the stellar disk. The rotation of this gas provides crucial information about the distribution of dark matter, since the gas orbits at speeds determined by the total gravitational mass of the galaxy, not just the visible matter. All of these different observations, at different wavelengths, combine to give us a comprehensive picture of Andromeda as a complex, multifaceted system. It's not just a collection of stars, but a living, breathing galaxy with ongoing star formation, complex dynamics, a violent past, and an eventful future ahead of it. Let's zoom in and think about what it might be like to actually be in the Andromeda Galaxy. Imagine you're on a planet orbiting a star in one of Andromeda's spiral arms, perhaps 50,000 light-years from the galactic center. Your night sky would be fundamentally different from Earth's. The spiral arm you're in would create a bright band of stars across your sky. But unlike the Milky Way as seen from Earth, you'd also see the bright glow of the galactic bulge off to one side, a concentrated sphere of yellowish stars marking the heart of the galaxy. Depending on where exactly in the arm you were located, you might see several nearby nebulae with your naked eye, vast clouds of glowing gas illuminated by hot young stars. On Earth, we can see a few nebulae like the Orion Nebula, but they're relatively faint. In a more crowded region of a spiral arm, you might have dozens of naked-eye nebulae, some spanning significant portions of the sky. The overall brightness of your night sky would likely be higher than Earth's, with more bright stars visible and a generally more crowded appearance. If your planet happened to be in the central bulge, the night sky would be absolutely spectacular. Stars would be packed so densely that you might see hundreds or even thousands of stars brighter than the brightest stars in Earth's sky. The night would never be truly dark. Even without a moon, the collective starlight would cast shadows. Stellar collisions and close encounters would be much more common in this environment, leading to exotic stellar phenomena rarely seen in the spiral arm. Of course, the same density that creates this spectacular view might also pose dangers. Supernovae would be more frequent in such a star-rich environment. While the distances would still be large enough that a nearby supernova wouldn't be immediately lethal to life, the higher frequency of these explosions could periodically bathe planets in elevated levels of radiation. It's possible that life might have a harder time getting started or surviving in the bulge compared to the spiral arms, though this is still a topic of scientific debate. One question that naturally arises when contemplating a galaxy of 1 trillion stars is, could Andromeda harbour life? The short answer is, we don't know, but the probability seems high. We now know that planets are common, with most stars hosting at least one planet. If we extrapolate this to Andromeda's 1 trillion stars, we're potentially looking at trillions of planets, even if only a tiny fraction are in the habitable zones of their stars, and only a tiny fraction of those actually develop life, and only a tiny fraction of those develop intelligent life. We could still be talking about millions or even billions of worlds with life in Andromeda alone. The question of whether any of those civilizations have developed technology and achieved the ability to communicate across interstellar distances is one of the most profound questions in science. If they exist, could we detect them? Unfortunately, Andromeda's distance of 2.5 million light-years makes this extremely challenging. Any radio signals we might detect would be 2.5 million years old, and they'd be incredibly faint by the time they reached us. Even a civilization broadcasting with the power of an entire star would produce a signal barely distinguishable from background noise at that distance. But the question goes deeper. If intelligent civilizations are common in Andromeda, they've had billions of years to develop. Some might have arisen when Earth was still a barren rock. What could a civilization accomplish with even 1 million years of technological development, let alone 1 billion? They might have spread throughout their galaxy, colonizing planet after planet, building megastructures that dwarf anything we can imagine, or they might have transcended their physical forms entirely, existing as beings of pure information or energy. These speculations venture into the realm of science fiction, but they're based on a real scientific question. The Fermi paradox asks why. If life is common in the universe and has had billions of years to develop, we haven't seen any evidence of it yet. There are many proposed solutions, ranging from the possibility that life is actually extremely rare, to the idea that advanced civilizations inevitably destroy themselves, to the notion that they're out there but deliberately avoiding contact with primitive species like us. We simply don't know. What we do know is that Andromeda, like all galaxies, contains the raw materials necessary for life. The heavy elements forged in stellar cores and supernovae, carbon, oxygen, nitrogen, phosphorus, sulfur, are all present in the interstellar medium. Organic molecules, the building blocks of life as we know it, have been detected in gas clouds throughout our own galaxy and presumably exist in Andromeda as well. The basic ingredients are there. Whether they've assembled themselves into living systems, and whether any of those systems have developed consciousness and technology, remains one of the great unknowns. Let's shift gears and talk about how we've come to know so much about Andromeda. The history of its study is a journey through the development of astronomy itself. Ancient observers noticed it as a faint blur, but had no way to understand what it was. They simply catalogued its position among the stars. In the 10th century, the Persian astronomer Abd al-Rahman al-Sufi described it in his Book of Fixed Stars, calling it the Little Cloud. This is the earliest surviving written record of the galaxy. For centuries, it remained a curiosity, one of many fuzzy patches in the sky that astronomers called nebulae, from the Latin word for cloud. The invention of the telescope in the early 1600s allowed closer examination, but still couldn't reveal its true nature. Even with telescopes, it appeared as an extended fuzzy blob rather than a collection of individual stars. The term nebula stuck, and Andromeda was known as the Andromeda Nebula for centuries. In the 18th century, the philosopher Immanuel Kant proposed a radical idea. What if some of these nebulae weren't clouds within our galaxy, but were instead island universes, entire galaxies like our own but at enormous distances? It was a prescient speculation, but without empirical evidence, it remained just that, a speculation. The debate about the nature of spiral nebulae continued into the early 20th century. The breakthrough came in the 1920 seconds through the work of Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, then the largest telescope in the world. Hubble studied Andromeda and was able to resolve individual stars in its outer regions. More importantly, he identified Cepheid variable stars, a type of star whose brightness fluctuates in a regular pattern. Henrietta Swan Leavitt had earlier discovered that there's a precise relationship between a Cepheid's period of variation and its intrinsic luminosity. By measuring how long it took Andromeda's Cepheids to brighten and dim, Hubble could determine their true brightness. By comparing this to how bright they appeared from Earth, he could calculate their distance. The result was stunning. Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way, which was thought to be about 100,000 light-years across. This single measurement revolutionized our understanding of the universe. The Milky Way wasn't the extent of creation. It was just one galaxy among many, and Andromeda was another entire galaxy, a separate island of billions of stars. Modern measurements have refined this distance to about 2.5 million light-years, nearly 3 times Hubble's original estimate. But the fundamental discovery remained: the universe was incomprehensibly larger than anyone had imagined. Hubble's observation is considered one of the most important in the history of astronomy, expanding the known universe by a factor of billions in a single stroke. Since then, our observations of Andromeda have grown progressively more detailed. Ground-based telescopes with ever larger mirrors and more sensitive detectors revealed more structure. The Hubble Space Telescope, launched in 1990 and named in honor of Edwin Hubble, has produced images of unprecedented clarity, resolving individual stars throughout much of the galaxy. In 2015, astronomers using Hubble created the largest and most detailed image of Andromeda ever made, a mosaic containing 1.5 billion pixels showing more than 100 million individual stars. You can zoom into this image and see star clusters, nebulae, dust lanes, all in exquisite detail. It's like having a cosmic Google Maps of another galaxy. Other space telescopes, observing in different wavelengths, have added layers to our understanding. The Spitzer Space Telescope's infrared observations revealed Andromeda's hidden structure, including those concentric rings of dust I mentioned earlier. The Chandra X-ray Observatory mapped its high-energy universe, finding thousands of X-ray sources. The Galaxy Evolution Explorer worked in ultraviolet, highlighting regions of active star formation. Radio telescopes on Earth mapped the distribution of hydrogen gas. Each observation at each wavelength adds another piece to the puzzle. Ground-based observations have also advanced dramatically. New techniques like adaptive optics, which uses flexible mirrors to compensate for atmospheric turbulence in real time, allow ground-based telescopes to achieve resolution rivaling space telescopes Spectroscopic surveys measure the motions of thousands of individual stars, revealing the dynamics of the galaxy in 3 dimensions. Astronomers can now map not just where stars are, but how they're moving, information crucial for understanding the galaxy's structure and evolution. One of the most remarkable recent developments is the use of computer simulations to model Andromeda's history and future. By plugging in the observed properties of the galaxy, its mass, rotation speed, star distribution, and more, astronomers can run the clock backward and forward, simulating what the galaxy looked like in the past and what it will look like in the future. These simulations have revealed that Andromeda has had a violent history, likely involving multiple mergers with smaller galaxies. They've also given us detailed predictions of how the future merger with the Milky Way will unfold. The simulations show that the merger won't be a simple head-on collision. Instead, the galaxies will approach at an angle, their spiral structures distorting as they interact gravitationally. Long tidal tails of stars will be pulled out, stretching across millions of light-years. The galaxies will pass through each other, then swing back for another pass, and another, gradually losing energy through gravitational interactions until they finally merge into a single elliptical galaxy. The entire process will take several billion years, a cosmic dance played out in extreme slow motion by human standards. These simulations aren't just theoretical exercises. They're tested against observations of other galaxy mergers occurring throughout the universe. The Hubble Space Telescope has imaged hundreds of merging galaxies, catching them at various stages from first approach to final coalescence. These observations validate the simulations and give us confidence that we understand the basic physics of galaxy mergers. When we predict what will happen to the Milky Way and Andromeda, we're not just guessing, we're applying well-tested models to a new situation. Now let's talk about something that might sound abstract, but is actually crucial to understanding Andromeda: dark matter. I mentioned earlier that dark matter makes up the majority of the galaxy's mass, but let's dig deeper into why we believe this and what it means. The evidence for dark matter in Andromeda comes primarily from studying how stars and gas orbit the galactic center. If the only mass in the galaxy were the stuff we can see, the stars and gas, then objects farther from the center should orbit more slowly, just like outer planets in the solar system orbit more slowly than inner planets. But that's not what we observe. In Andromeda, as in virtually all galaxies, the orbital speeds remain roughly constant even in the far outer reaches of the galaxy, a phenomenon described by what astronomers call a flat rotation curve. The only way to explain this is if there's a huge amount of invisible mass distributed throughout and around the galaxy, providing extra gravitational pull that keeps the outer stars moving faster than they otherwise would. How much dark matter? Current estimates suggest that the dark matter halo of Andromeda might extend for 1 million light-years or more from the galactic center, several times larger than the visible disk. The total mass of this halo could be 10 times greater than the mass of all the visible matter in the galaxy. We're literally surrounded by this stuff, swimming in it, and yet we have no direct evidence of what it actually is. The leading theory is that dark matter consists of subatomic particles that don't interact with electromagnetic radiation, meaning they don't emit, absorb, or reflect light. They pass right through normal matter almost as if it weren't there, interacting only through gravity and possibly through the weak nuclear force. Physicists have given names to hypothetical dark matter particles like WIMPs, weakly interacting massive particles, and axions. But despite decades of searching with increasingly sensitive detectors, we haven't directly detected any of these particles yet. The failure to detect dark matter particles is actually one of the great frustrations of modern physics. We know from gravitational evidence that dark matter exists. We can map where it is by studying how it affects the motion of visible matter and how it bends light from more distant objects through gravitational lensing. But we can't directly detect the particles themselves. It's like knowing someone is in a room with you because you can hear their footsteps, but no matter how hard you look, you can't see them. Some scientists have proposed alternative theories. Maybe there's no dark matter at all, and instead our understanding of gravity is incomplete. Perhaps gravity behaves differently on galactic scales than on smaller scales, and that's why galaxies rotate the way they do. These theories, collectively called modified Newtonian dynamics, or MOND, can explain galaxy rotation curves without invoking dark matter, but they struggle to explain other observations, like the behavior of galaxy clusters and the pattern of temperature fluctuations in cosmic microwave background. The overwhelming consensus among physicists is that dark matter is real, even if we haven't yet figured out exactly what it is. For Andromeda, the dark matter halo is not just an interesting curiosity, it's fundamental to the galaxy's existence. Without it, the galaxy couldn't hold together. The visible matter alone doesn't have enough gravity to prevent stars from flying off into intergalactic space. The dark matter halo acts like an invisible cosmic glue, holding everything together. It also plays a crucial role in how galaxies form in the first place. In the early universe, dark matter clumped together first, creating gravitational wells into which normal matter could fall. The visible galaxies we see today formed inside these pre-existing dark matter halos. Understanding dark matter is one of the primary goals of modern physics and astronomy. Experiments deep underground, shielded from cosmic rays and other interference, are trying to detect the rare occasions when a dark matter particle might interact with normal matter. Particle accelerators like the Large Hadron Collider are trying to create dark matter particles by smashing protons together at enormous energies. Space telescopes are looking for the signature of dark matter particles annihilating each other, which should produce gamma rays. So far, these searches have come up empty, but they're becoming more sensitive with each passing year. Many physicists believe we're on the verge of a breakthrough. When that breakthrough comes, when we finally figure out what dark matter actually is, it will revolutionize our understanding of the universe. It might point to new physics beyond the standard model, to new forces and particles we haven't yet imagined. And Andromeda, along with countless other galaxies, will have played a crucial role in leading us to that discovery, because it was by studying how galaxies rotate that we first realized something was missing from our understanding of the cosmos. Let me take a moment to address the sheer scale of what we're discussing. When you look up at Andromeda, you're seeing a galaxy that spans 220,000 light-years. But what does that actually mean? Let's try to wrap our heads around it by starting small and building up. The Earth is about 40,000 kilometers around the equator. If you could drive a car at highway speeds without stopping, it would take you about 17 days to circumnavigate the globe. The distance from Earth to the Moon is roughly 384,000 kilometers, about 10 times Earth's diameter. Light covers this distance in 1.3 seconds. The Sun is about 150 million kilometers from Earth, a distance called an astronomical unit, or AU. Light from the Sun takes 8 minutes and 20 seconds to reach us. If you could somehow drive to the Sun at highway speeds, it would take you about 170 years. The distance to Neptune, the outermost major planet in our solar system, is about 30 AU. Voyager 1, the most distant human-made object, launched in 1977 and has been traveling at about 17 kilometers per second, is currently about 150 AU from the Sunday. It's taken more than 45 years to get that far, and it still hasn't left the solar system's gravitational influence. The nearest star to the Sun, Proxima Centauri, is 4.24 light-years away, or about 268,000 AU. At Voyager 1's speed, it would take about 75,000 years to get there, and that's just the nearest star. The Milky Way galaxy contains hundreds of billions of stars spread across a disk, 100,000 light-years in diameter. To cross the Milky Way at Voyager 1's speed would take about 1.8 billion years. Now multiply that distance by 2.2. That's how big Andromeda's disk is. And remember, this is just the visible disk. The dark matter halo extends much farther, perhaps 5 or 10 times larger still. The scale is so vast that it genuinely defies human comprehension. We can state the numbers, we can do the math, but truly grasping what those numbers represent is beyond our evolved capacity. Our brains developed to navigate landscapes on Earth, to judge distances of meters and kilometers, not light years and megaparsecs. And yet, here we are, tiny beings on a small planet, discussing the structure of a galaxy millions of light years away. We've measured its mass, mapped its structure, predicted its future. This is one of humanity's greatest achievements. Not just the technical accomplishment of building telescopes and instruments, but the intellectual achievement of learning to think on these scales, of developing the mathematics and physics to describe the universe at all scales from the subatomic to the cosmic. There's something almost absurd about it when you stop to think about it. A species that evolved to pick fruit and hunt prey on an African savanna has figured out the mass of a galaxy containing 1 trillion stars located 2.5 million light-years away. We've done this using light that's been traveling since before our species existed, analyzing it. With instruments we've built based on laws of physics we've discovered over just the last few centuries. It's a testament to the power of the scientific method, to systematic observation, hypothesis formation, and testing. And we're not done. Every year, our observations become more detailed, our simulations more sophisticated, our understanding deeper. The James Webb Space Telescope, launched in late 2021, is now observing the universe in infrared with unprecedented sensitivity. It's already revolutionizing our understanding of distant galaxies, and it will undoubtedly reveal new secrets about Andromeda as well. Future telescopes, even larger and more capable, are in development. The quest to understand our cosmic neighborhood continues. Before we wrap up, I want to come back to the question I posed at the beginning. What does it mean that you can see Andromeda with your naked eye? We've spent this entire documentary exploring the galaxy's structure, its history, its future, its place in the cosmos. We've discussed measurements and observations, dark matter and black holes, mergers and collisions, but sometimes the most profound truths are the simplest ones. When you stand outside on a dark night and look up at that faint smudge of light, you're looking at an entire galaxy. You're seeing the combined light of 1 trillion suns, photons that have been traveling through space for 2.5 million years. Every one of those photons was emitted by a star, traveled across the empty void between galaxies, made it through Earth's atmosphere, and landed on your retina. You're physically connected to that distant galaxy through those particles of light. You're not just observing it from afar. You're touching it, in a very real sense, through the exchange of photons. And it's not just Andromeda. Every star you see in the night sky is touching you with its light. Every distant galaxy captured by telescopes is sending photons on multi-billion-year journeys that occasionally end in a camera's detector or a human eye. We're not separate from the cosmos. We're part of it, embedded in it, connected to everything we can see through the fundamental forces of physics. This connection goes even deeper. As I mentioned before, the atoms in your body were forged in stars. The oxygen you breathe, the carbon in your DNA, the calcium in your bones, all of it was created in stellar cores through nuclear fusion and scattered into space by supernovae. You are literally made of stardust, a collection of atoms that spent billions of years cycling through multiple generations of stars before ending up in your body. When you look at Andromeda, you're not looking at something alien and foreign. You're looking at a place made of the same stuff you are, governed by the same laws of physics, filled with the same types of stars that created you. There's a perspective that comes from contemplating these cosmic scales that I find both humbling and empowering. Humbling because it reveals just how small we are in the grand scheme of things. Earth is a tiny speck in a solar system that's a tiny part of a galaxy that's just one of hundreds of billions in the observable universe. Your entire existence, everything you've ever experienced, every person you've ever known, all of human history, from the first stone tools to the latest space probes, all of it has occurred on a single planet orbiting an ordinary star in the outer suburbs of an ordinary galaxy. And yet, it's also empowering, because despite our small size and brief lifespans, we've figured out how the universe works. We've measured distances to galaxies, determined the masses of black holes, predicted collisions billions of years in the future. We've traced the history of the cosmos from the Big Bang to the present day. A species of apes that only learned to write a few thousand years ago has decoded the secrets of the universe. That's extraordinary. So yes, Andromeda is big. Incomprehensibly, staggeringly big. But its size doesn't diminish us. If anything, it elevates us, because we're the ones asking the questions, making the observations, building the theories. We're the ones who looked at a faint smudge in the sky and figured out what it really is. We're the universe becoming conscious of itself, matter and energy organized in such a way that it can contemplate its own existence and place in the cosmos. As we come to the end of this cosmic journey, I want to encourage you to go outside on the next clear, moonless night and find Andromeda yourself. Use a star chart or astronomy app to locate it. Look for the constellation Andromeda, find the fuzzy patch, and take a moment to really see it. Don't just glance at it and move on. Stare at it for a while. Let your eyes adjust to the darkness. See if you can make out any structure, any hint of the vast spiral galaxy hidden in that faint glow. And while you're looking at it, think about everything we've discussed. Think about the trillion stars, each one a sun in its own right. Think about the countless planets that must orbit those stars, the possible worlds where life might have emerged. Think about the supermassive black hole lurking at the center, warping space and time around it. Think about the dark matter halo, invisible but ever present, holding the whole system together through gravity. Think about the galaxy's journey toward us, the inevitable collision billions of years in the future that will reshape both our galaxies into something new. Think about the light itself, the photons entering your eyes that began their journey when our ancestors were barely human, that have traveled across millions of light years to end their existence in your retina. You're not just looking at Andromeda, you're connected to it through those particles of light. You're part of the same universe, made of the same atoms, governed by the same laws. And if you feel small, remember, you're the one doing the looking. You're the one capable of understanding what you're seeing. The galaxy is huge, and you are small, but you have something it doesn't: consciousness, curiosity, the ability to wonder and question and learn. In a universe of unconscious matter and energy, that makes you extraordinary. So look up at Andromeda and marvel. Marvel at its size, its beauty, its complexity. Marvel at the fact that you can see it at all. Marvel at the journey of science and discovery that transformed it from an unexplained blur into an understood and measured galaxy. And marvel at yourself, a thinking, conscious being capable of contemplating the cosmos and your place within it. If this journey through the Andromeda Galaxy has expanded your mind, hit that like button and leave a comment telling me what aspect fascinated you most. Were you blown away by the scale? Intrigued by dark matter? Excited about the future collision with the Milky Way? I want to hear your thoughts. And if you haven't already, subscribe to Dark Cosmos Theory and ring that notification bell, because we're just getting started exploring the mysteries of the universe. There are countless cosmic wonders still to discover, and I want you along for every journey. Remember, every time you look up at the night sky, you're looking back in time. You're seeing light from stars and galaxies as they were in the past, sometimes the distant past. Andromeda's light is 2.5 million years old, but that connection across time and space is real. The photons are real, the galaxy is real, and your ability to understand and appreciate it, that's real too. The universe is vast beyond comprehension, filled with wonders we're only beginning to discover. But it's also knowable. With patience, careful observation, and rigorous thinking, we can unlock its secrets. We can measure the unmeasurable, understand the incomprehensible, and find our place among the stars. This is dark cosmos theory, where we don't just accept the universe as it is, we question it, explore it, and reveal the hidden truths that lie waiting in the cosmic darkness. Until next time, keep looking up, keep asking questions, and never stop wondering about the magnificent universe we call home. But before we close this chapter, there's so much more to explore about Andromeda that we haven't even touched on yet. We've covered the basics, the grand scale, the inevitable collision. But let's dive deeper into some of the most fascinating aspects of this galactic giant that reveal just how complex and mysterious our neighbor truly is. Let's start by talking about something that might sound technical, but is actually one of the most important discoveries about Andromeda: its stellar populations. When I say the galaxy contains 1 trillion stars, it's easy to imagine them all being similar, just countless copies of the same thing. But the reality is far more interesting. Andromeda contains stars of every type imaginable, from massive blue supergiants burning hundreds of times, brighter than our Sun, to tiny red dwarfs that will outlive the universe's current age. From ancient metal-poor stars formed in the galaxy's youth, to brand new stars still surrounded by the dusty disks from which planets form. Astronomers classify stars by their spectral type, a system based on their surface temperature and color. The hottest stars are O-type stars, blazing blue-white and so massive that they burn through their fuel in just a few million years. Then come B-type stars, still blue but slightly cooler. A-type stars are white, F-type are yellow-white, G-type stars like our Sun are yellow, K-type stars are orange, and M-type stars are red and cool. Each type has different properties, different lifespans, different fates. In Andromeda's spiral arms, you'll find an abundance of hot young O and B-type stars. These are the stars that light up the arms in brilliant blue, making them stand out in photographs. They're massive, typically 10 to 100 times the mass of our Sun, and they live fast and die young. An O-type star might only live for a few million years before exhausting its hydrogen fuel and exploding as a supernova. This sounds like a long time to us, but remember that our Sun has been shining steadily for 4.6 billion years and has another 5 billion years to go. These massive stars burn out in the blink of an eye by cosmic standards. When these massive stars explode, they don't just disappear. They seed the interstellar medium with heavy elements created in their cores through nuclear fusion. Elements like carbon, oxygen, nitrogen, silicon, iron, all the elements heavier than hydrogen and helium, were created in stars. Some were made in the normal fusion process in stellar cores. Others, the really heavy ones like gold and platinum and uranium, were created in the extreme conditions of supernova explosions or in collisions between neutron stars. Every atom of oxygen you breathe was created in a massive star that exploded before our solar system formed. Every atom of iron in your blood was forged in a stellar core. Every atom of calcium in your bones came from a star. You are, quite literally, the universe made flesh, a collection of atoms that have cycled through multiple generations of stars over billions of years. When you look at Andromeda, you're looking at the same process that created you, still ongoing, stars forming and dying, creating and scattering the building blocks of planets and life. In contrast to the young, hot stars in the spiral arms, Andromeda's central bulge is dominated by older, cooler stars. These are primarily K and M-type stars, along with many evolved stars that have exhausted their core hydrogen and swelled into red giants. The bulge has a yellowish color in photographs, the combined light of billions of these older suns. Star formation in the bulge is much less active than in the spiral arms. Most of the bulge stars formed billions of years ago in an early burst of star formation when the galaxy was young and gas was more abundant. By studying the colors and spectra of stars in different parts of Andromeda, astronomers can reconstruct the galaxy's star formation history. They can determine when and where stars formed, how the rate of star formation has changed over time, and how the galaxy has evolved. What they've found is that Andromeda hasn't formed stars at a steady rate. There have been peaks and valleys, times when star formation surged, and times when it slowed to a trickle. Some of these variations are thought to be triggered by galaxy mergers. When Andromeda absorbed a smaller galaxy, the gravitational disturbance would have compressed gas clouds, triggering bursts of intense star formation. Evidence for these past mergers is written in the galaxy's structure, in the warps and asymmetries of its disk, in the streams of stars in its halo that are the remnants of tidally disrupted satellites. Andromeda is not a pristine galaxy that formed and then remained unchanged. It's a constantly evolving system shaped by billions of years of interactions and mergers. One of the most intriguing stellar populations in Andromeda is found in its globular clusters. These are dense, spherical collections of stars, typically containing hundreds of thousands to millions of stars packed into regions just tens of light years across. Globular clusters are among the oldest objects in the universe. The stars in them are ancient, formed in the early universe when it was only a few billion years old. They contain very few heavy elements, formed before generations of supernovae had enriched the cosmos with carbon, oxygen, and iron. Andromeda has an impressive collection of globular clusters, somewhere between 450 and 500 of them identified so far. That's actually fewer than the Milky Way, which has around 150 to 200. Wait, no, I need to correct that. The Milky Way has around 150 to 200, while Andromeda has more, 2 to 3 times as many. These clusters orbit through Andromeda's halo on long, elliptical paths, taking hundreds of millions of years to complete a single orbit around the galactic center. Studying Andromeda's globular clusters provides insights into the galaxy's early history. The distribution of clusters, their ages, their chemical compositions, all of these properties carry information about the conditions in the early universe and how Andromeda formed. Some clusters show evidence of being captured from smaller galaxies that Andromeda consumed, adding another chapter to the story of galactic cannibalism. Inside these globular clusters, the environment is unlike anything in the spiral arms. Stars are packed so tightly that interactions and near collisions are relatively common. This leads to exotic stellar phenomena rarely seen elsewhere. Blue stragglers, for instance, are stars that appear younger and bluer than they should be for the cluster's age. They're thought to form when two stars collide and merge, creating a single, more massive star that burns hotter and bluer. X-ray binaries, where a normal star orbits a neutron star or black hole and matter streams from the normal star onto the compact object, are also common in globular clusters. The density of globular clusters also affects any potential planets. While planets probably formed around stars in these clusters just as they do around stars in less crowded environments, their long-term survival is questionable. Close encounters with other stars could perturb planetary orbits, ejecting planets from their systems or sending them plunging into their parent stars. If you lived on a planet in a globular cluster, your night sky would be spectacular beyond imagination, filled with thousands of bright stars, but your world would also be subject to occasional gravitational disturbances as other stars passed nearby. Now, let's talk about something that's revolutionized our understanding of Andromeda in recent years: the discovery of stellar streams in its halo. These streams are the remnants of smaller galaxies that Andromeda has torn apart through tidal forces. As a small galaxy orbits around Andromeda, the gravitational pull is stronger on the near side than the far side. This differential force, called a tidal force, stretches the smaller galaxy, pulling stars out in long trails that wrap around Andromeda. Deep surveys of Andromeda's outer regions have revealed multiple such streams, delicate arcs of stars tracing the paths of defunct satellites. The most prominent is called the Giant Southern Stream, a massive structure containing the shredded remains of a galaxy that Andromeda consumed sometime in the last few billion years. By studying the properties of stars in this stream, their positions, motions, and compositions, astronomers can work backward to figure out what the original galaxy looked like when the merger occurred and how it has affected Andromeda's structure. These streams are important for several reasons. First, they're direct evidence that galaxies grow by consuming smaller companions, supporting our theoretical models of galaxy formation and evolution. Second, they provide a way to map the distribution of dark matter in Andromeda's halo. The streams are affected by the gravity of all the matter in the galaxy, both visible and dark. By modeling how the streams move and evolve, astronomers can infer where the dark matter is and how much there is. Third, the streams tell us about the population of small galaxies in the early universe. Many of the galaxies Andromeda has consumed were probably too small and faint to be seen directly if they still existed as separate entities today. But by studying their remnants in the stellar streams, we can learn about a population of galaxies that would otherwise be invisible to us. It's like galactic archaeology, piecing together the past from the fossils left behind. The discovery of these streams has also revealed something unexpected. Andromeda's halo is far more extensive than previously thought. Stars from disrupted satellites are found at distances of hundreds of thousands of light-years from the galactic center, much farther than the visible disk. This means that in a sense, Andromeda is even larger than the 220,000 light-year diameter I mentioned earlier. If you count the halo, the galaxy extends for 500,000 light-years or more, and its dark matter halo might extend for 1,000,000 light-years. This has interesting implications for the Milky Way-Andromeda collision. The two galaxies' halos might already be overlapping. We might already be inside Andromeda's dark matter halo, and Andromeda might be inside ours. The collision, in a sense, has already begun. It's just that the collision of the halos, which are mostly empty space and dark matter, is invisible and has minimal effect on the stars and planets. The dramatic part, when the stellar disks interact, is still billions of years away. Let's shift our focus to another fascinating aspect of Andromeda, its dust. When most people think of galaxies, they think of stars, but dust plays a crucial role that's often overlooked. The dust grains in Andromeda are tiny, smaller than the particles in cigarette smoke, but they have an outsized impact on the galaxy's appearance and evolution. Dust does several things. First, it absorbs and scatters starlight, making regions of the galaxy appear dimmer and redder than they would otherwise. This effect, called extinction, has to be accounted for when astronomers try to measure the properties of stars and the total light output of the galaxy. If you don't correct for dust extinction, you'll underestimate how many stars there are and how bright they actually are. Second, dust re-radiates the energy it absorbs as infrared light. This makes dusty regions of the galaxy glow in infrared even if they're dark in visible light. Some of the most intense infrared emission comes from regions of active star formation, where young stars are still embedded in the dusty clouds from which they formed. Infrared observations essentially allow us to see through the dust and detect star formation that would be completely hidden in visible light. Third, and perhaps most importantly, dust provides the surfaces on which molecules can form in interstellar space. In the cold vacuum of space, it's difficult for atoms to collide and stick together to form molecules, but on the surfaces of dust grains, atoms can meet and bond, building up more complex molecules. This is how hydrogen atoms combine to form molecular hydrogen, H2, which is the primary constituent of star-forming clouds. It's also how more complex molecules form, including organic molecules containing carbon. Astronomers have detected hundreds of different molecules in interstellar space, ranging from simple two-atom molecules like carbon monoxide to complex organic molecules with dozens of atoms. Some of these molecules, like amino acids and sugars, are the building blocks of life as we know it. While we can't study the interstellar medium of Andromeda in as much detail as we can our own galaxy due to the distance, there's no reason to think it's fundamentally different. The same types of molecules that exist in the Milky Way almost certainly exist in Andromeda too. The distribution of dust in Andromeda is not uniform. It's concentrated in the spiral arms and in rings, those concentric structures I mentioned earlier that were discovered in infrared observations. The leading theory is that these rings were created by a collision with another galaxy, possibly M32, sometime in the last few 100 million years. The collision would have sent density waves rippling through Andromeda's disk, compressing gas and dust into rings and triggering waves of star formation. This brings up an interesting point. Galaxies are not static objects. They're dynamic, constantly changing, responding to gravitational perturbations, both internal and external. The spiral arms themselves are density waves, patterns that rotate through the galaxy like the arms of a spinning lawn sprinkler. Individual stars and gas clouds pass through the arms, slowing down as they enter, then speeding up as they leave. The pattern persists, even though the material forming it is constantly changing. Understanding these dynamics requires sophisticated computer simulations. Astronomers create models of galaxies as collections of millions or even billions of particles, each representing a clump of stars or gas. They let these simulations run forward in time, calculating the gravitational forces between all the particles at each step. It's computationally intensive, requiring supercomputers and months or even years of processing time. But the results can be spectacular, showing how spiral arms form and persist, how bars develop in galactic centers, how galaxies respond to interactions and mergers. These simulations have been crucial for understanding Andromeda. They've helped explain its structure, its rings, its warps and asymmetries. They've shown how a collision with M32 could have created the features we observe. And they've given us detailed predictions of what the merger with the Milky Way will look like, allowing us to create visualizations showing how the galaxies will appear from Earth's perspective as they approach, interact, and finally coalesce. Now I want to talk about something that connects Andromeda directly to the search for life in the universe: exoplanets. We now know that planets are common in the universe. Observations with telescopes like Kepler and TESS have shown that most stars have at least one planet, and many have multiple planets. If we extrapolate this to Andromeda's trillion stars, we're potentially looking at trillions of planets. Of course, not all of these planets would be habitable. Many would be gas giants like Jupiter, far too large and lacking a solid surface. Others would orbit too close to their stars, baked by intense radiation, or too far, frozen solid. But even if only a tiny fraction are in the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface, we're still talking about billions of potentially habitable worlds in Andromeda alone. The problem is that we can't detect individual planets in Andromeda. The galaxy is simply too far away. When we detect exoplanets around stars in our own galaxy, we're typically looking at stars within a few thousand light-years of Earth at most. Andromeda is 2.5 million light-years away. The light from an Earth-sized planet orbiting a sun-like star in Andromeda would be utterly overwhelmed by the star's light, impossible to detect with current technology. But we can make statistical predictions. If planet formation works the same way in Andromeda as it does in the Milky Way, and there's no reason to think it doesn't since the physics is the same, then Andromeda should have a planet, population similar to ours, scaled up by its larger number of stars. This means somewhere in the vicinity of 1 trillion planets, with perhaps tens of billions in habitable zones. Now, the existence of habitable planets doesn't automatically mean life. We don't know how likely it is for life to arise on a planet with the right conditions. This is one of the biggest unknowns in astrobiology. Is life common, arising on most planets where conditions permit? Or is it incredibly rare, requiring such a precise combination of circumstances that Earth might be one of the only inhabited worlds in the galaxy, or even in the entire observable universe? The truth is, we don't know. We have a sample size of 1, Earth. Until we detect life elsewhere, either in our solar system, on worlds like Mars, or Europa, or around other stars, or in other galaxies, we can't answer this question definitively, but the sheer number of potential habitable planets is staggering. Even if life is very rare, even if only 1 in a billion habitable planets develops life, there could still be tens of life-bearing worlds in Andromeda. And if intelligent, technological life is even rarer, perhaps only arising on 1 in a billion life-bearing worlds, there could still be dozens of technological civilizations in Andromeda. Of course, these numbers are completely speculative. We're stacking unknown probabilities on top of unknown probabilities. But the point is that given the immense number of stars and planets, even very low probabilities don't necessarily mean we're alone. If civilizations do exist in Andromeda, they've had plenty of time to develop. Andromeda is old. Its oldest stars formed more than 12 billion years ago. Earth, by comparison, is only 4.5 billion years old. There could be civilizations in Andromeda that are billions of years older than us, that arose when our solar system didn't even exist yet. What could such a civilization accomplish given billions of years of development? This is where we enter the realm of speculation, but it's informed speculation based on physics and our understanding of what's possible. A civilization millions or billions of years more advanced than us might have spread throughout its galaxy, colonizing world after world, perhaps terraforming planets to make them habitable or constructing artificial habitats in space. They might have developed technologies we can barely imagine, harnessing the energy of entire stars, manipulating matter at the atomic level, perhaps even engineering space and time itself. Some scientists have proposed that very advanced civilizations might build megastructures large enough to be detectable from other galaxies. A Dyson sphere, for instance, is a hypothetical structure that completely surrounds a star, capturing all of its energy output. Such a structure would be warm, glowing in infrared, but not in visible light. Astronomers have actually looked for such signatures in nearby galaxies, including Andromeda, searching for stars that are bright in infrared but dim or invisible in visible light. So far, they haven't found any convincing candidates, but the search continues. The absence of obvious signs of advanced civilizations in Andromeda or elsewhere in the universe is actually a puzzle known as the Fermi paradox. If life is common and some fraction of life-bearing worlds develop intelligent, technological civilizations, and if some of those civilizations expand outward, colonizing other worlds, then given the age of the universe, we might expect to see evidence of them everywhere. The fact that we don't see such evidence, that the universe appears empty of obvious alien artifacts or signals, is surprising and demands explanation. There are many proposed solutions to the Fermi paradox. Maybe life is much rarer than we think. Maybe intelligent life is rarer still. Maybe technological civilizations tend to destroy themselves before they can spread across the galaxy. Maybe they're out there, but deliberately hiding, following some sort of cosmic non-interference policy. Maybe they exist but use communication methods we haven't thought of or aren't looking for. Maybe they've transcended physical form and exist in ways we can't detect. Or maybe, sobering as it sounds, we really are alone, or at least among the first, the universe still young enough that intelligent life is only now beginning to arise. We don't know the answer. But the question itself is profound. When you look at Andromeda, you're looking at 1 trillion stars, trillions of potential worlds, billions of years of history. If life exists there, even if we never detect it, even if we never communicate with it, the mere fact of its existence would be significant. It would mean we're not alone. It would mean the universe is alive, not in one place but in many, consciousness and complexity arising wherever conditions permit. Let's talk about something more concrete, the supermassive black hole at Andromeda's center, in greater detail. I mentioned earlier that it weighs somewhere between 100 and 200 million solar masses, making it far more massive than the Milky Way's central black hole, Sagittarius A*, which weighs about 4 million solar masses. This enormous difference is puzzling and might tell us something about the different evolutionary histories of the two galaxies. How do supermassive black holes form? This is actually one of the outstanding questions in astrophysics. We know that stellar mass black holes, those with masses of a few to a few dozen times the Sun's mass, form when massive stars collapse at the end of their lives. But supermassive black holes are millions or billions of times more massive. They can't form directly from stellar collapse. They must grow over time, but how? One possibility is that they start as stellar mass black holes that grow by accreting matter from their surroundings. Every bit of material that falls into a black hole adds to its mass, and in the dense, gas-rich environment of a galaxy's center, there's plenty of material available. Over millions and billions of years, a stellar mass black hole could grow into a supermassive one through continuous accretion. But there's a problem with this scenario. Accretion onto black holes is limited by radiation pressure. As matter spirals into a black hole, it heats up due to friction and emits intense radiation. This radiation pushes back on the infalling matter, limiting how fast the black hole can grow. This limit is called the Eddington limit, and for a stellar mass black hole, it means the black hole can at most double its mass every few tens of millions of years. That sounds fast, but even starting from a 100 solar mass black hole 13 billion years ago, you couldn't grow it to 100 million solar masses by the present day. The universe simply isn't old enough. This suggests that supermassive black holes either started out much more massive than stellar mass black holes, perhaps forming directly from the collapse of massive gas clouds in the early universe, or they grew partly through mergers with other black holes. When two galaxies merge, their central black holes eventually merge as well, creating a single, more massive black hole. Andromeda's large black hole might be the result of multiple such mergers over its history. The dynamics of how black holes merge is fascinating. When two galaxies collide, the black holes don't immediately fall together. They're embedded in their respective galactic cores, and those cores sink toward the center of the merged system over hundreds of millions of years through a process called dynamical friction. Think of it like two massive objects moving through a sea of stars. The gravitational interactions with surrounding stars gradually slow the cores down, causing them to spiral inward. Eventually, the two black holes get close enough that their mutual gravity dominates, and they begin to orbit each other in a tight binary. As they orbit, they emit gravitational waves, ripples in the fabric of space-time that carry away energy. This causes the orbit to shrink, bringing the black holes closer together, which makes them orbit faster, which makes them emit stronger gravitational waves, which shrinks the orbit further. It's a runaway process that ends with the black holes merging in a final burst of gravitational waves so powerful that it briefly outshines all the stars in the universe combined, at least in gravitational wave energy. We've detected such events with the LIGO and Virgo gravitational wave detectors, though so far only for stellar mass black hole mergers. The merger of two supermassive black holes would be at a different frequency, too low for LIGO to detect, but potentially observable with future space-based detectors like LISA, the Laser Interferometer Space Antenna. When Andromeda's black hole merges with the Milky Ways in a few billion years, the gravitational waves will wash over whatever. Civilizations exist in the local universe, carrying the news of our galactic merger to anyone capable of detecting them. The region immediately around Andromeda's supermassive black hole is one of the most extreme environments imaginable. Close to the event horizon, gravity is so strong that light itself is bent into circular or spiral paths. Time dilation becomes significant. Clocks closer to the black hole tick slower than clocks farther away. If you could somehow survive in this environment and watch from just outside the event horizon, you'd see the rest of the universe blue-shifted and sped up, stars evolving in fast forward, while from the perspective of distant observers, you'd appear frozen in time, moving slower and slower as you approach the horizon. Stars orbit the black hole at tremendous speeds. The closest ones complete orbits in just a few million years, despite being light years away from the center. Some stars pass so close to the black hole that they experience a significant tidal forces. If a star gets too close, within what's called the tidal disruption radius, the difference in gravitational pull between the near and far sides of the star becomes so large that it tears the star apart. Half of the star's material gets flung out into space, while the other half falls into the black hole, creating a brilliant but brief flare as it's heated to millions of degrees. Astronomers have observed tidal disruption events in other galaxies, and they provide valuable information about the masses and properties of supermassive black holes. We haven't seen one in Andromeda yet, but statistically, they should occur every few tens of thousands of years in a galaxy like this. We might just be unlucky, or more likely, one happened in the past, but we weren't looking at the right time, or one will happen in the future and we'll be watching. Despite its enormous mass, Andromeda's black hole is currently relatively quiet. It's not actively consuming large amounts of material, and it's not producing the bright jets and intense radiation characteristic of active galactic nuclei or quasars. This is actually typical for nearby galaxies. Most supermassive black holes go through cycles of activity and quiescence. During active phases, when there's a lot of gas and dust falling in, the black hole shines brilliantly, sometimes outshining the entire rest of the galaxy. During quiet phases like Andromeda is experiencing now, the black hole is barely noticeable except through its gravitational effects on nearby stars. What triggers these cycles of activity? Usually, it's a supply of gas falling toward the galactic center, often delivered by a galaxy merger or interaction. When two galaxies collide, gravitational torques can funnel gas inward, feeding the central black hole and triggering an active phase. This suggests that Andromeda might have been more active in the past, perhaps during or shortly after the merger that created its dust rings, and it might become active again during the future merger with the Milky Way, as gas from both galaxies funnels inward. Let's zoom back out and think about Andromeda's place in the larger cosmic web. Galaxies are not randomly distributed throughout the universe. They're organized into a hierarchical structure: groups, clusters, superclusters, and filaments. The Milky Way and Andromeda, along with about 50 smaller galaxies, make up the local group, which is itself part of the Virgo supercluster, also called the Laniakea supercluster, a massive structure containing tens of thousands of galaxies spread across hundreds of millions of light-years. The local group is located in the outskirts of this supercluster, in a relatively low-density region. If we lived in the core of a massive galaxy cluster, the night sky would be filled with bright nearby galaxies, dozens or even hundreds visible to the naked eye. But we'd also be exposed to much higher levels of radiation from the hot gas that fills. Galaxy clusters and galaxy-galaxy interactions would be much more frequent. Life might be more difficult in such an environment. Our location in a small group in a cosmic backwater is actually quite fortunate. It's quiet enough that galaxies like the Milky Way and Andromeda can evolve relatively undisturbed for billions of years, allowing time for complex structures like spiral arms to develop and persist. If we were in a denser environment, mergers would be more frequent, and galaxies would likely be disrupted and transformed into ellipticals much sooner. The motion of the local group through space is influenced by the gravitational pull of surrounding structures. We're falling toward the Virgo cluster, the massive collection of galaxies at the heart of our supercluster, at a speed of about 400 kilometers per second. At the same time, we're being pulled by other massive structures, including the Great Attractor, a concentration of mass beyond the Virgo cluster, whose nature is still not fully understood because it lies in a direction obscured by the Milky Way's disk. These cosmic motions remind us that nothing in the universe is truly stationary. Everything is moving, falling, orbiting, influenced by gravity on all scales. Andromeda is moving toward us, we're moving toward Virgo. Virgo is moving toward the Great Attractor, and the entire local supercluster is being pulled toward an even larger structure called the Shapley supercluster. It's motion within motion, a cosmic ballet choreographed by gravity. Understanding these large-scale structures and motions has been one of the major achievements of cosmology in recent decades. By mapping the positions and velocities of thousands of galaxies, astronomers have reconstructed the large-scale structure of the nearby universe, showing how galaxies trace out filaments and walls surrounding vast voids almost empty of galaxies. This structure arose from tiny density fluctuations in the early universe, which grew over billions of years through gravitational collapse. Andromeda's position in this cosmic web is part of its identity. It's not just an isolated galaxy, it's a node in a vast network, connected to everything else through gravity and through shared history, stretching back to the Big Bang. When we study Andromeda, we're studying not just one galaxy but our entire local universe, learning about the forces and processes that shaped everything we can see. Now, I want to address something that might seem abstract but is actually crucial to understanding Andromeda: redshift and blueshift. I mentioned earlier that Andromeda is blue-shifted, meaning it's moving toward us. But let me explain what this really means and why it's significant. Light is a wave, and like all waves, it has a wavelength, the distance between consecutive peaks. Different wavelengths correspond to different colors. Red light has a longer wavelength than blue light. When an object emitting light is moving toward you, the wavelengths get compressed, shifted toward the blue end of the spectrum. When it's moving away, the wavelengths get stretched, shifted toward red. This is the Doppler effect for light, analogous to how the pitch of a siren changes as an ambulance passes you. When astronomers look at distant galaxies, they almost always see red-shifted light. This is because the universe is expanding, and expansion carries distant galaxies away from us. The farther away a galaxy is, the faster it's receding, and the greater its redshift. This relationship between distance and redshift, discovered by Edwin Hubble, is one of the key pieces of evidence for the Big Bang. But Andromeda is blue-shifted. Its light is shifted toward shorter wavelengths, indicating it's approaching at about 110 kilometers per second. This might sound paradoxical. If the universe is expanding, how can Andromeda be moving toward us? The answer is that expansion of space only dominates on large scales, between galaxy groups and clusters separated by hundreds of millions or billions of light years. On smaller scales, within groups and clusters, gravity is strong enough to overcome expansion. Think of it like this. Imagine raisin bread dough rising in an oven. As the dough expands, the raisins move apart from each other. But if two raisins happen to be stuck together, they'd stay together even as the dough around them expands. Gravity is what sticks the Milky Way and Andromeda together, keeping them bound even as the larger universe expands around us. The blue shift of Andromeda was first measured in 1912 by Vesto Slipher, well before anyone understood what it meant. At the time, astronomers didn't even know Andromeda was a separate galaxy. They thought it was a nebula within the Milky Way. The fact that it was blue-shifted was curious, but didn't seem particularly significant. Only later, after Hubble proved Andromeda was a separate galaxy, and after the expansion of the universe was discovered, did the full implication become clear. Andromeda and the Milky Way are on a collision course. Modern measurements have refined this. Andromeda isn't moving directly toward us. It's approaching at an angle. The 110 kilometers per second is just the radial velocity, the component of its motion along our line of sight. It also has a tangential velocity, motion across our line of sight, that's harder to measure because it requires detecting the tiny motion of the galaxy against the background sky over years or decades. Recent measurements with the Hubble Space Telescope have managed to do this, showing that Andromeda is not just approaching but also moving slightly to one side. This matters for predicting the collision. If Andromeda were heading straight for us, it would be a direct hit. But with a tangential component to its motion, the collision will be more of a glancing blow, at least initially. The galaxies will approach, pass by each other, then swing back for another pass. This is actually typical for galaxy mergers. Direct head-on collisions are rare. Most are prolonged interactions with multiple passages. The blue shift of Andromeda is actually unusual in a cosmological sense. If you look at a random galaxy in the universe, it will almost certainly be redshifted, receding from us due to expansion. Only a handful of very nearby galaxies are blue shifted, and Andromeda is by far the largest and most luminous of them. In a sense, it's special, a rare example of a major galaxy moving toward us rather than away. This brings up an interesting point about cosmic perspective. From Earth, we see Andromeda approaching. But from Andromeda, hypothetical astronomers would see the Milky Way approaching. Neither perspective is more correct. It's all relative. What matters is not that one galaxy is stationary and the other is moving, but that they're moving toward each other, that the distance between them is shrinking. Let me spend some time on a topic that fascinates me. What Andromeda can teach us about the Milky Way. This might seem backward. Shouldn't we learn about the Milky Way by studying the Milky Way? But there's a problem. We're inside the Milky Way. We see it from within, edge on, our view obscured by dust, unable to see its overall structure clearly. Andromeda, by contrast, we see from outside, tilted at a convenient angle that lets us see its full spiral structure. By studying Andromeda, we can learn about what spiral galaxies in general are like, and we can infer what the Milky Way probably looks like to a distant observer. For instance, the Milky Way's spiral structure was a matter of debate for decades. We knew we lived in a disk galaxy based on the band of light across our sky, but we couldn't directly see the spiral arms because we're embedded in them. By mapping the positions of star-forming regions and young star clusters, astronomers gradually pieced together the arm structure, but there were competing models and uncertainties. Studying Andromeda helped resolve some of these questions. By understanding how spiral arms form and what features they contain, astronomers could better interpret the observations of our own galaxy. We now think the Milky Way has a four-arm spiral structure, possibly with a bar, based partly on what we've learned from galaxies like Andromeda. Similarly, by studying how dust is distributed in Andromeda, how star formation proceeds in its arms, how its halo is structured, we gain insights applicable to the Milky Way. Andromeda is in many ways a template, showing us what a large spiral galaxy looks like and how it behaves. The differences between Andromeda and the Milky Way, meanwhile, tell us about the range of variation possible within the spiral galaxy class. One of the most important things we've learned from Andromeda is that large galaxies have complex assembly histories. Andromeda didn't form in a single event and then remain unchanged. It's been built up over billions of years through mergers with smaller galaxies, and this process has shaped its current structure in subtle ways. The stellar streams in its halo, the warps in its disk, the peculiar distribution of its globular clusters, all of these are fossil evidence of past interactions. The same is almost certainly true of the Milky Way. We're finding evidence of past mergers in our own galaxy's halo, streams of stars with distinct motions and compositions that betray their origin in now defunct dwarf galaxies. The most famous is the Sagittarius stream, the remnant of the Sagittarius dwarf galaxy that the Milky Way is currently tearing apart. By analogy with Andromeda, we expect our galaxy has undergone similar mergers throughout its history, growing larger by consuming smaller neighbors. This changes how we think about galaxies. They're not static objects that formed in the early universe and have remained unchanged. They're dynamic, evolving systems, constantly interacting with their environments, growing through mergers shaped by billions of years of cosmic history. Every galaxy has a story, and Andromeda's story is written in its structure for those who know how to read it. Let's talk about the future of Andromeda observations. What new things might we learn in the coming years and decades? Several upcoming and planned telescopes will dramatically improve our view of Andromeda and our understanding of its properties. The James Webb Space Telescope, launched in December 2021, is already revolutionizing astronomy. Webb observes primarily in infrared, and its sensitivity and resolution are unprecedented. For Andromeda, Webb will be able to study star-forming regions in incredible detail, identifying individual young stars still embedded in their natal clouds. It will be able to probe the chemical composition of gas clouds, detecting molecules and determining the abundances of different elements. And it will be able to study the galaxy's stellar populations more precisely, distinguishing different types of stars and determining their ages. Future ground-based telescopes are also in the works. The extremely large telescope, currently under construction in Chile, will have a mirror 39 meters in diameter, making it the largest optical telescope ever built. With such a massive aperture, it will be able to resolve features in Andromeda in extraordinary detail, potentially even detecting individual red supergiant stars throughout the galaxy. It will also have advanced spectrographs that can measure the motions of thousands of stars simultaneously, providing a three-dimensional map of how the galaxy rotates and how its stars move. Other planned missions will study Andromeda in different ways. X-ray observatories will map its high-energy universe more completely. Radio telescope arrays will probe its magnetic fields and trace its distribution of gas. Gravitational wave detectors, as they become more sensitive, might even detect the merger of stellar mass black holes or neutron stars in Andromeda, individual events from another galaxy. All of these observations will add to our understanding. We'll learn more about Andromeda's star formation history, about the distribution of its dark matter, about its interactions with satellite galaxies, about the properties of its supermassive black hole. Each new piece of data will refine our models and might reveal unexpected features that challenge our current understanding. One exciting possibility is that we might detect individual stars in Andromeda that explode as supernovae. Supernovae are rare. A typical galaxy might produce one every century or so. But Andromeda is constantly monitored by automated surveys looking for transient events, sudden changes in brightness that might indicate a supernova, a variable star, or other interesting phenomenon. When a supernova does occur, telescopes around the world will quickly turn to observe it, gathering data on the explosion and learning about the star that died. Supernovae are important for several reasons. They're one of the main ways that heavy elements are returned to the interstellar medium, enriching it for future generations of stars. They can trigger new star formation by compressing nearby gas clouds. They provide insights into stellar evolution, particularly the late stages of massive stars. And certain types of supernovae, type Ia supernovae, are remarkably consistent in their brightness, making them useful as standard candles for measuring cosmic distances. By studying supernovae in Andromeda, we can test our models of stellar evolution and supernova physics. We can learn about the galaxy's star formation rate, since supernova frequency is linked to how many massive stars are being produced. And we can refine our understanding of cosmic distance scales, since Andromeda's distance is known accurately from other methods, providing a test of the Type Ia supernova standard candle technique. Another area of future research is the interaction between Andromeda and its satellites. As telescopes become more sensitive, we'll likely discover more ultra-faint dwarf galaxies orbiting Andromeda, galaxies so dim and diffuse that they've escaped detection so far. Each new discovery adds to the census of Andromeda's family and provides constraints on models of dark matter and galaxy formation. The reason this matters for dark matter is subtle but important. Our models of how structure forms in a universe dominated by dark matter predict that large galaxies should be surrounded by many small dark matter halos, each potentially hosting a small galaxy. The exact number and properties of these satellite galaxies depend on the nature of dark matter, on whether it's cold, moving slowly, or warm, moving faster, and on other details of particle physics beyond the standard model. For years, there seemed to be a missing satellites problem. Simulations predicted thousands of small dark matter halos around galaxies, like the Milky Way and Andromeda, but we only saw a few dozen satellite galaxies. This discrepancy suggested either that our dark matter models were wrong or that most small halos don't form visible galaxies for some reason. Recent discoveries of ultra-faint dwarfs have partially resolved this tension. We're finding more and more satellites as our surveys become more sensitive, suggesting that they're there but just very faint. But we still haven't found as many as the simulations predict, and it's possible that most small dark matter halos are actually dark in every sense, containing little or no stars. Understanding this is crucial for understanding dark matter, and Andromeda provides an excellent laboratory since we can see it from outside and potentially detect its full satellite population more easily than we can the Milky Ways. I want to spend a few moments on the philosophical and existential implications of Andromeda. When you really sit with the fact that there's another galaxy, a vast island of 1 trillion suns, hanging in our sky, visible to the naked eye, approaching us for an eventual merger billions of years from now, it changes your perspective on existence. We live in a universe of staggering scale and age. Andromeda has been shining for more than 10 billion years. Stars have been born and died in countless cycles. Planets have formed, perhaps life has arisen, civilizations may have come and gone, all in a galaxy we can see as a faint smudge. The light reaching us from Andromeda left that galaxy when our ancestors were just beginning to walk upright on the African savanna, before we had language, before we had art, before we were truly human in the modern sense. And yet here we are, a species that learned to walk upright, that developed language and culture and technology, that built telescopes and spacecraft, that figured out the nature of Andromeda and predicted its collision with our galaxy billions of years hence. We are, as far as we know, the only beings in the Milky Way capable of understanding this. We might be the only beings in the local group, though if there are civilizations in Andromeda, they've probably figured out the same things. There's something profound about being aware of your cosmic context, about knowing that you live in a galaxy that's part of a group, that's part of a supercluster, that's part of the cosmic web, about knowing that your galaxy is on a collision course with another, about understanding that the universe has a history stretching back 13.8 billion years and a future extending trillions of years into the future. This awareness doesn't make our daily lives any easier. It doesn't help pay the bills or resolve conflicts or cure diseases, but it provides perspective. It reminds us that we're part of something vast and ancient and ongoing. It connects us to the cosmos in a deep way, not just as observers, but as participants, as fragments of the universe that have become conscious and capable of understanding their origins and destiny. When you look at Andromeda, you're looking at your galaxy's future partner, the galaxy will merge with to form something new. You're looking at 1 trillion suns that may harbor countless worlds, some of them possibly bearing life. You're looking at a system that has evolved over billions of years and will continue to evolve for billions more. You're looking at a neighbor in the truest sense, close enough to see with your eyes, close enough to study in detail, close enough that our destinies are linked, and you're looking at mystery. Despite everything we've learned about Andromeda, despite all the observations and measurements and simulations, there's still so much we don't know. What exactly happened in its past to create the features we see today? What is its dark matter made of? Are there planets with life? Have civilizations arisen and perhaps fallen? What will the merged Milky Galaxy look like in detail? What will the night sky look like during the merger? These questions don't have answers yet. Some of them might never have answers, at least not in our lifetimes. But the ability to ask them, to wonder, to imagine, that's part of what makes us human. We're not content with just seeing the faint smudge. We want to know what it is, how it works, where it came from, where it's going. We want to understand our place in the cosmos. Andromeda offers us that opportunity. It's close enough to study, large enough to be spectacular, complex enough to be endlessly fascinating. It's a teacher, showing us how spiral galaxies work, how dark matter shapes them, how they evolve through mergers, how they'll look billions of years from now when they collide. It's a mirror, reflecting back at us a picture of what the Milky Way probably looks like from outside. It's a neighbor, bound to us by gravity, approaching for an eventual merger that will reshape both galaxies. Most of all, it's a reminder of scale, of how vast the universe is, how small we are in comparison, and yet how remarkable it is that we can understand it at all. We're tiny beings on a tiny planet, but our minds can encompass galaxies. We live for decades, but we can understand processes that take billions of years. We're made of atoms, but we can understand how those atoms were forged in stars like those in Andromeda. So the next time you're under a dark sky, take a moment to find Andromeda, look at that faint blur, and remember everything we've discussed. Remember the trillion stars, the countless worlds, the spiral arms, the dark matter halo, the supermassive black hole, the satellite galaxies, the dust and gas, the ongoing star formation, the ancient globular clusters, the stellar streams, the approach toward us, the eventual collision. Remember that you're seeing light that's 2.5 million years old, that you're looking back in time, that you're connected to that distant galaxy through the photons entering your eyes. And remember that every slight number, every measurement, every image, every simulation representing centuries of human effort, countless hours of observation, brilliant insights from thousands of astronomers and physicists working across generations to decode the cosmos. When you look at Andromeda, you're not just seeing a galaxy, you're seeing the culmination of human curiosity and ingenuity, our drive to understand the universe we inhabit. If you've made it this far in this deep dive into the Andromeda Galaxy, thank you. Thank you for caring enough about the cosmos to spend this time learning about our nearest galactic neighbor. I hope I've given you a new appreciation for that faint smudge in the sky, for the galaxy that's been watching over Earth for millions of years and will one day merge with our own. Make sure you're subscribed to Dark Cosmos Theory, because we're going to continue exploring the mysteries of the universe together. Hit that like button if this video expanded your cosmic perspective, and drop a comment telling me what aspect of Andromeda fascinated you most. Was it the sheer scale, the dark matter mystery, the inevitable collision with the Milky Way, the possibility of life? Let me know. Remember, we're all made of stardust, all part of the same cosmos, all connected to Andromeda and every other galaxy through the atoms in our bodies and the laws of physics that govern everything. Keep looking up, keep asking questions, and never lose that sense of wonder at the universe we're privileged to explore. This has been Dark Cosmos Theory. Until next time, stay curious about the cosmos.